Hi guys, welcome back to the Astro Imaging channel. Tonight's presentation is by David Alt, and it's on advanced PixInsight pixel math operations. But before I turn it over to David Alt, I just want to remind you guys on YouTube you can subscribe to us to get our new videos, or you could join us on Google Plus to get into these live hangouts and ask your questions live. For the people who are not in this live session, just type them into the Q&A and we'll get to them. We'll call them right out to David as we go. But right now I'm going to hand it over to Josh, who is going to introduce our new image spotlight. We're going to spotlight an image each week. So Josh, go right ahead.
Thanks, Adam. So one thing we were excited about doing to bring some new content to the show was give everyone an opportunity to share their images through the Astro Imaging channel. And we got some great responses last week, and a lot of really great images came in. Last week we had, let's see, it was Bill McLaughlin took the image of the week last week, and we're going to change that over to the weekly image spotlight. And if we select your image, it'll be the banner for the week on the front page of the Astro Imaging channel. For this week, we're going to continue to pick from the same pool, and we picked Sean Harrison's image of M42. And part of what we're going to do with the weekly image spotlight is have the person who actually captured the image share some details about how they captured the image, possibly talk about a little bit of the science going on in there, and anything that they ran into whenever they were processing the image. So if you take a look at the screen, you can see the M42 that Sean Harrison took, and he's going to just describe what he did to capture that image for a few minutes.
Hi guys, this is Sean. Thanks, Josh. So this was a relatively new telescope for me. I've been using a 10-inch SCT, so with a focal reducer that comes out to around 1700 millimeter, and I never could get all of M42. So I was really happy to get this scope because it has a little bit wider field of view, and I really didn't want diffraction spikes. So it's a Schmidt-Newtonian. So it's a Newtonian with a spherical mirror that has a corrector plate in the front of it, like a regular Schmidt-Cassegrain, to correct for the field curvature. And so overall, I'm pretty happy with this scope. It has some field curvature out around the edges. You'll see the stars sort of flare away, and I've yet to get a field flattener for it. But so far, I'm really happy with the scope. So I live in an orange zone, and on a good night, I can see the Milky Way fairly decently. So darker than some, but not really dark. So this image was taken through the Meade SN6, and was taken with a beta modified Canon XS with no filters. So this is all 5-minute exposures. I think there was 3 hours and 50 minutes of total exposure. And then I also took an additional 20 exposures at 10 seconds for the core detail. It was all processed in Photoshop, so stacked in Deep Sky Stacker, which is free, and then I took the raw resulting stack and processed it in Photoshop. I used a lot of the techniques that Scott Rosen uses with the layer masking for screen invert and a lot of the curves and levels tricks that he has in his tutorial. And I processed the luminance completely separately. So basically you duplicate the image and then work on the luminance for all of your stretching and sharpening and contrast and star reduction. And then you bring back in the color. Basically blur the color and then use your black and white as your luminance for all your detail. I spent a lot of time trying to get the inner dust between the M42 and the Running Man to come out. And I was pretty happy with it. I don't think my flats were exactly right, but overall it came out pretty well. and I was pretty happy with the color balance that I got out of it. So my stars were pretty good for 5-minute exposures, which is something that I was not getting with the 10-inch SET. So overall, I was really happy with the way this came out because it was the first time that I could get all of M42 and the Running Man in the same frame without having to create a mosaic, which just causes lots of problems. So, and to the right of M42, there was a huge halo on the star that's just to the right there of the outer loop, and I used some of what David is going to talk about to try to get rid of that. So I created like a little mask using circles and tried to reduce the size of it. You can barely see a little purplish halo around that bright star, so there was some left over. I'm sure in PixInsight David would have really taken care of it. So now there's only a smaller halo around there, but you do get some halos from the corrector plate, and then up at the very, very top left, people often talk about Schmidt ghosting, and so there's a little blue area up at the very top left, and that's actually a Schmidt ghost from that bright star on the right of the loop there. But overall, I was really happy with it, and thanks for choosing my image as the spotlight of the week.
Yep, you're welcome, Sean. It's an awesome image. If there's one thing we love here on the Astro Imaging channel, it's dark reflection, dust, and nice brown, dirty, dusty images. So it's a really good, great resolution down to the core of M42. The colors are beautiful in the Running Man, and it was just it's really cool to see, and also nice to be able to share some great images that aren't necessarily captured with high-end CCDs and $10,000 scopes. So really great work on that. So we will post about this week, and we will also put out a post for next week's weekly image spotlight, and look forward to seeing whatever images are added to the pool throughout the week. So now I am going to go ahead and turn it over to David, and he's going to present on advanced PixInsight pixel math operations. Thanks, David. Looking forward to it.
Hey guys. So first I want to let you know I'm not the end-all be-all expert here. There's some guys over on the PixInsight forums and certainly the developers that know a lot more about this than I do, but I have picked up a few things, and if you find these things useful, that's absolutely great. I want to help as much as I can, so hopefully everyone can get a little bit from this presentation. All right, Adam, can everyone see the screen there?
Yes, I can.
All right. So why would you use pixel math? Pixel math is a very powerful tool that gives you access to all sorts of features that otherwise would require scripts or plug-in development. In PixInsight, that's PCL, or potentially standalone programs to use. I use it regularly for blending images with various functions, averaging, max, min, hot pixel removal, altering or creating masks, testing calibration data, doing linear gradient-based clipping or merging, noise reduction, doing simple things like drawing lines or circles or other geometry, and removing unwanted artifacts like star halos. So there's a few syntax rules for pixel math. There are symbols and expressions. The symbols are basically just variables, just like you'd see in any program language. They have to be defined separately outside of the expression. For every assignment made in the expression space, you have to have a corresponding symbol. Symbols can be signed values, but they can only be constants if you put them in the symbol box. This is the equivalent of initializing variables. There's also a few built-in symbols like the $T. This particular one is used to reference the active or new instance view. The T stands for target. Symbols need to be separated by commas, although I think you can separate them with semicolons as well, but I generally use commas. Expressions are where the math is done. There's all sorts of available functions, from logs to sines to specific kind of statistical functions like by-weight midvariance. The Pixel Math engine can handle parenthetical equations, so you can put as many parentheses in there as you want. If you don't happen to know what the order of operations of a particular math function is, just use some parentheses to make sure. Symbols are available for most functions like addition, subtraction, multiplication, powers, things like that. Expressions, you can actually have multiple expressions within the expression field. You have to separate these by semicolons. So, for example, you might define one function that is trying to determine the radius from a central point. And then you'll use that radius value in another expression. And we'll talk a little bit more about that later. So pixel math basically runs in a big loop over each pixel in the active view. So for example, if you use the expression 0.5 times $t, this will multiply, we'll step over in a big loop over every pixel in the design, multiply whatever that value is by 0.5, and then return it. It can be returned to that same window, or it can be used to create a new window based off of the previous image. There are functions available for determining where you are in the image loop, like the X and Y functions. So you can actually use these to target specific locations in the image. There are also functions that are non-loop based, like determining the mean or the median, the by-weight midvariance. These operate on the entire image and return a single result. Some of these functions, like mean, have dual purposes. You can operate it on an image or on a set of values, typically delineated with commas. So you can do a lot of math just in one line on the basic pixel math form, but there's a button on the form that pops up the expression editor. And you can do a lot more advanced stuff in here, and you can see a picture of what I have on the right that shows, a fairly complex set of functions all ending up in one value. So if you're going to do anything a little more advanced, it's best to bring up the expression editor. You get quick access to, if you see on the very right, image, symbols, functions, operators, punctuation, all that sort of stuff. You can just double click on it and it'll add it in to wherever your cursor is at in the actual expression. You can also check the syntax of your expressions without running it on the entire image. So, if you hit OK and you just run it on the image and you get to a particular step in the process, then it may fail and you won't know that. But if you hit the parse button on the bottom of the form in the expression editor, you can check the syntax and everything beforehand. There's also syntax highlighting. You can see functions are highlighted in blue, images are bolded, integers and real values are in red, things like that. So it automatically does some syntax highlighting. So these are the examples I was going to cover tonight. I'm going to look at some image blending stuff. I'm going to cover weighted linear blends. This is sometimes called an alpha blend, or a variation called a weighted average. I'll cover some of the Photoshop equivalent blends. These are, on the layer blending on Photoshop, you can do all sorts of different functions with an opacity in between them. I'm going to cover how some of those can be done in pixel math. Star mask combinations, doing things like generating a synthetic color channel. I'll cover some rendering processes, like inserting lines and circles. Cross sections is a pretty interesting one. You can actually take a slice out of your image and actually look at what all the values look like across that. I'll look at some hot pixel removal and noise reduction with pixel math, and I'll go over the star halo removal tutorial that I had posted on the Cloudy Nights forum, and look at some manual calibration evaluation. And I'll put this presentation out there. I've put a bunch of the equations and stuff in the presentation that everyone can look at. So I'll post this on the Google Plus page after we're done here, so you can use this as a reference. Let's get in. So before I move forward, are there any questions
I haven't seen any questions yet. I do want to remind the people who aren't in our live area here, you can type your questions into Q&A or comments, and we'll get right to you. We'll just call them right out to David. So, thanks, David.
Sure. So I'm actually going to be using some of Sean's data here. Let me flip this around. And we're going to, let's see, we'll go to some of the simpler stuff first here. So the first one I want to look at is alpha blending, or weighted averaging. So these are 3 images from the Hubble Space Telescope, downloaded off of their archive. And I'll just stretch these guys and so we can see them here. All right. And for a simple test, I may just want to say I want to generate a synthetic luminance out of these. I may just want to take the nitrogen-2 and the helium-2 and just take elements from that. So I'm just going to go through here. Let me start from scratch. And what I'm going to do is bring up the expression editor, and I'm going to look through my image list, and I'm going to bring up the helium-2 and the nitrogen-2, and I'm going to put in some functions around this. I'm going to multiply one by some variable, and I'm going to then multiply the other one by the inverse of that. So that means as A approaches 1, you'll get nothing but this image, and as A approaches 1 over here, you won't get any of this. So you'll always get an equal amount from either image. So if A is at 0.5, then 1 minus A will be at 0.5 over here. So we're going to put an even blend in there. I'm going to put in a variable A, and I'm just going to assign it a value of 0.5. And then I can hit the parse expression, and you can see it produces some information about whether it's parsed. If I get something wrong in here, say I remove a parenthesis and parse it, you'll see it fails. It says there's a mismatch left parenthesis. It puts a little marker in front of the one that's missing something. That looks pretty good. So you can see that fills out the rest of the form here. So I have A times the He, the helium-2, and 1 minus A times the N2. In the destination section, you can actually tell it whether you want to replace or create a new instance. In this case, say I'm creating a synthetic luminance, I'm going to have it create a new image. I want it to still base the size and everything off of an active window, though, so you can see how it says down here, image ID is auto, target is based on the target image and width, and the same for the color space, whether it's grayscale or color. So it's going to pull all that information from the active window, which you can see this one's active over here. So if I hit the apply button, it'll give me a new image. And you can already see that it has some elements of both. Get that out of the way. So let me shrink these down a bit. So you can see this little protrusion in here is more prominent in this picture, not as prominent as it is in the N2 picture here, over here, in that area, but it still sticks out a bit more. So we're getting some portion of both in there. Get rid of the previews. So I'm going to remove this image, and now I'm going to do it again, but I'm just going to change the variable, and I'm going to make it 0.2. So now that says that only 20% of the result is going to be from the helium, and that means 80% is going to come from the nitrogen. So now if I look at this, it looks a lot more like the N2 image than it does the helium-2. And this can be extended. So, for example, say I don't want to do I call that an alpha blend. Say I actually want to do synthetic luminance from all three images. I can remove these constants, and I'll go back into the expression editor again, and I'll bring up one more image. I'll bring up the O3. When I can directly apply weightings to these, date. So now I've got 0.4 plus 0.4 is 0.8 plus 0.2 is 1. So I'll get an average out of this, but it's going to be weighted towards the helium and the N2 without much O3. So if I do the same thing again, stretch the image, you can see it still has some elements of the N2. That little protrusion is still there, but not as pronounced as it is in the N2 image, more than the helium-2, and certainly a lot more than the O3. So it's a good way to kind of balance out if you're looking for specific features. You can use this kind of method for targeting one image over another. Any questions yet, Adam?
Not yet.
All right. So let me bring up some star masks. So in this case, with Sean's image here, I was having problems getting all the stars to show up. So I ran star mask 3 different times, and you can see, one time captured Allen attack here. So it shows up as one very large star. The next pass, I got some of the brighter ones in the field, but not quite all of the small ones. And the last pass catches just some of the fainter ones in there. And I want to make one star mask out of this, right? So if I bring up Pixel Math again, I'll just reset all the values. What I really want from this is the maximum of all of them. So I can just put in a max function. And I can either, in this case, I'm just going to write over one of the images. So you can see now that all the stars from the previous star masks now show up in this one. You can see the difference there. So you have access to all sorts of functions to do this sort of stuff, right? So if you pull down on the list of functions, you can see max is in here. And if you click on it, you can see you can do it based off of values or just one image if you just want the maximum value in an image. In this case, it's going to operate over each pixel of the main active image. And for each pixel there, it's going to look at the maximum from those 3 images and return that as the result. So I use this pretty frequently, especially if there's a wide variance in star sizes that you're trying to mask out appropriately.
I have a question real quick. Is there a difference in that and adding each of those images to one of the other to get the mask? If you were to just add each mask to...
There is a difference, and it depends on whether you have stars overlapping or not. So in that particular case, I didn't really have any overlaps. But you'll essentially get the data from one star added on top of the other. And I really want the actual just shape of the star mask here replicated in the other image rather than adding the values. If I've got, another bright star next to this one or something, I don't want it to scale over the value of one and start getting truncated, which is why
Right. Okay.
the max function there. Yeah.
And I have a question, and I may be drawing a blank, but what would be a maximum blend mode in Photoshop? Is there one?
There is. It's brighten.
Brighten.
Or lighten.
Lighten mode. Okay, duh. Yeah. All right. Yeah, that was a blank I was drawing.
Yeah. There's also one for minimum, which is useful as well. That's darken, I think. And I'll actually go through a few Photoshop equivalents here. So let me do another blending trick here. So I'll do a synthetic green. This is data from the Sloan Digital Sky Survey. So this is M82, and I'm just going to take those, and in this case I'm just going to take the red data. Let me just rename these here so it's just red and green. So I'm going to take the red data and just assign it to the red channel. I'm going to take the green data, assign it to the blue channel in this case, and then I'm going to use this function here to create my image. And you can see it's actually two expressions. So the first one is creating a temporary green value, and in this case I'm taking 90% of the green image and blending it with 10% of the red image to get the green value. And then I actually do this function where I can do an alpha blend between that temporary green value and this minimum function. So this is looking to see if the green value is brighter than the average of the red and green together. If it is, then I'm going to get the red and green value. Likewise, if the red and green average together is greater than the temporary green value, then I get the temporary green value. Everything parses okay. In this case, I want to create a new image, and you can see the sizes are going to be based off of the image height and width, but I've actually changed the color space. So you can see that I've also turned off the use RGBK expression. So now it'll use all the separate, it'll do all the color processing separately. And it'll store it in an RGB image. So when I hit apply, I get that out of it. It's not particularly colorful. You'd want to stretch it a bit. Let me bring up the curves real quick and push the saturation so you can see a bit more. But you can see that there is some red and some bluish colors in there, but it doesn't look just straight teal. It looks kind of a bluish color tint to it by doing that min function as part of the blending. Okay, so now let's look at some Photoshop blending examples here. So I'll bring up the same Hubble data here. Now you notice that I've stretched the data. This is because the Photoshop relies on typically a midpoint value of some sort. So a lot of their functions are revolving around 0.5 to determine whether something is multiplied or divided or subtracted or added or things like this. So most of the Photoshop ones want to work on already stretched data. So I'm going to take a couple of these and rename them a bit here. I'll take the 03 and say it's going to be our top layer, and the N2 is going to be our bottom layer. And if I want to do a multiply on those, then really it's just top times bottom. But in Photoshop, you have the opacity function where you can vary how much of that result shows up in the final combined layers. So I put in an alpha blend here to take the bottom versus the result of my multiplication In this case, what would be 100% in Photoshop would be a value of 1, and you can see that's going to give me nothing but the multiplication results. Whereas if I did a 50% blend, then I would get half of the result from the multiplication and half from the bottom layer. So I'm going to create a new image here. So you see this darkens the image a little bit relative to this guy. In fact, if I stretch it the same as this one, it looks about the same. You can see the interiors and everything are darkened in this one relative to the other one. And some of the little faint areas in here show up as a bit darker in here as well. But if I go through and set it all the way to 1, you see it darkens it a lot more. So this is the straight multiplication result out of those two. And you can replicate any of the Photoshop filters. There's a screen filter. Oops. You can see this is actually doing the inversion of both multiplied by each other and then inverting it again. This is inversion because the range of the image goes from 0 to 1. So you effectively make it, your values from 0 to 1 now go from 1 to 0 before you do the multiplication, and then you invert that back again. There's a little function in PixInsight. There's actually an inversion character, so you can use the tilde, and that'll get the same result. So I could actually do this, and there's another one where I don't remember what the order of operations is for the tilde relative to everything else, but I could do the same thing in all these cases, right? And I should get the same result, which it looks like it is. Now in my presentation I have most of these documented. You can find them online. I think on the Wikipedia entry for Photoshop blending modes, you can find all the math for these as well. Some of them get kind of complex. You can see this one is switching based off of the value of the bottom image. So if it's less than 0.5, then it does one thing. If it's greater than 0.5, it does something else. Here's your darken function. So this is a minimum between the two images. So we set this to 1. So you can see that the darker area of the nitrogen 2 is much darker than the interior of the O3. So we get most of the N2 result at the interior. But then all these kind of little specks in here on the edges are a little bit darker than the ring of this one, so we end up getting those showing up in the ring portion. Lighten is the max. Oops. Get a new image instead. So here you can see that I get a lot of the brightness from the interior with the bright ring of the nitrogen 2 here. It kind of washes out some of the ring elements here because parts of this ring are brighter than these darker edges in here. But you can change that a little bit. Say you only wanted part of that blend mode. You could do 80% or something like that. Addition, subtraction, all those are pretty straightforward. Division, you can see that mostly what's happening is you're just multiplying or dividing the top by the bottom. Some of the other ones like soft light, these get a lot more complex. You can see there's a lot of stuff going on. Again, it's another test against the 50% mark of the bottom image, and then you have this long convoluted inversion of images with multipliers and stuff like that. All right. So any question on some of the Photoshop blend equivalents?
None yet.
All right.
David, I have one real quick.
Sure.
So how do they work if you are working either in grayscale or RGB? If you're looking for pixel values, does it just do each channel independently? So go ahead.
No, it doesn't. So if I bring up that function again, so like here it's doing a test against 0.5. When it does that against an image and it's a color image, it's actually going to take the luminance value. I think it takes the CIE L component to do a test against one single value. If I wanted to do it against multiple colors, I could use the single expression off, and then I could have separate ones for each. But in general, if you're doing a test against a single value, it will turn that RGB value into essentially its grayscale counterpart to do the test against. But then once you get over it, yeah. All right. So I like this one, the removing purple stars. So this image was another one from the Cloudy Nights posts. Let me get rid of that guy. So I've created a star mask for this one already, and you can see that in this image some of the stars are purple using the standard sulfur, hydrogen, oxygen combination method of the color data. So what I'm going to do is try to reduce that. So I'm going to apply the star mask and let it operate on only the stars. So the star mask is still in effect, but I've made it not visible anymore. And I've seen this one out there. There's a couple variations, but I'll explain essentially what each of them are doing. In this case, I'm not doing anything to the red or blue channels. Those stay entirely exactly as they are. This function means I'm taking the target image and I'm taking the red channel from that. In this case, it can actually be simplified. If you're doing separates, you don't actually need the 0 in there. It understands that if you're doing this in the blue expression field, that it's going to pull the blue channel. But for the green channel, what I'm going to do is I'm going to look at the minimum of the red and blue channels and compare it to the green channel. And if red and blue together, which if you combine those is a purple color, if it's greater than the green, meaning I have more purple than I have green, then I'm going to replace it with that minimum value. Otherwise, I leave it alone. So by doing this replacement for anything where you've got more red and green than red and blue than green, you can effectively remove the purple color from these. So I've set this to replace the current image, but because the mask is in place, it should only affect the stars. So I'll zoom in a little bit here. And so you can see that some of the stars here actually changed from, I'll undo and redo here. Zoom in on some of these a bit more. You can see that they change from purple to somewhat whitish. It's clear my star mask could be a little bit better. I'm not really catching any of these really, really small stars, but most of them in the field of view do actually improve. All right. Any questions on that particular one?
David, I have a couple questions on this one.
Sure.
So one thing that I always thought would be cool is and I think that maybe CCD Stack does this, but if you can process an RGB image field, or star field, where all you have is your RGB stars, would you be able to do some kind of if-and function where if you looked at your target image that had a lot of the narrowband stars, or even if you're just doing this for like a RGB image where you blow out a lot of your stars, can you look for values over a certain number, like maybe over 220, and say anytime I see a value over 220, replace it with image A, and have image A have more colorful stars down to the core?
Yeah, absolutely. It's something you can do with that. I mean, it would be pretty straightforward. In this case, instead of doing a compare here, you would do, I'd be looking for my green. Actually, I would do this in one pass. I'm assuming your SHO image would be color as well as your star image, right? And so I'd really just look for if the value at a particular point is greater than 5, what's that work out to be in 0 to 6555? So 240, you said?
Mm-hmm.
0.935. If it's greater than that, then I would take the value from the star image. Otherwise, I would just give it the current image, right? So if I had an image with stars in it, this would be whatever that image was named.
So this would operate the same way and look at the grayscale value of both images?
That's correct.
Okay.
Well, in this case, it would just be comparing the grayscale image to a constant value.
Okay.
But even then, if you did a comparison of, some other value that wasn't a constant, it would still do the grayscale of the active window, the target window, as the comparison. And this is another one you'd want to have a star mask in place, so that you're only replacing stars, so that parts of your nebula, like these portions of the nebula over here might be over 0.935 in the core, so you don't want to replace those, right?
Mm-hmm.
All right, any other questions on that part? I forgot, there's some other ways to do this, and I'll show a couple here. In this case, I'm actually assigning red, green, and blue. You can see I left these without the brackets on there, so it knows that it's the red channel, so I don't have to assign it. But in the green field, I actually take the channels and reassign them to RGB values, so it's a little easier for me to see once I get to this section of the code. But here you see I assign a temporary green value, and I just make it a 50% blend of the red and blue, and then I just take the max of the actual green value versus the temporary green value. If I zoom in here again and apply this guy, you can see the same thing. This one's a little different. I'm not taking the minimum, I'm taking the average, but it effectively works the same way. I think this one does a better job of balancing out the actual brightness of the stars than taking the minimum value does, which is why I prefer this particular method. All right. So now we're going to draw some lines here. I'm going to flip the image around. So if you want to draw some lines, say just for reference, or you want to do some sort of annotation, you can do that with Pixel Math as well. Here's a very simple function. I've assigned a symbol with an X location at 685, and all I'm doing is checking to see if the current image in the loop that PixelMath runs through, if that X location is equal to the X location I specified, then I want to make the pixel value 1. If it's not, every other X location in the image gets whatever the value was before. So the point of this is that it's going to end up drawing a vertical line at X location 685, which is close to the center of the image. If I mouse over this at the bottom of the screen, down here you can actually see there's some readout of the pixel values, and you can see that says 685. So that allows you to draw lines on your image. You can do horizontal ones. If I just wanted to, I don't actually need a value there. I want to draw a line at Y value of 300. I can draw a line horizontally. You can do more complex lines and stuff like that, which I'll show you here as well. This is the function for a circle. There's actually an easier way to do this, but I put this in here so you could see the math of it. This is just the equation for a circle, just x squared plus y squared equals r squared. I just rearranged it looking for r, and I've allowed some offsets in here. So you can see that I'm taking the x value minus the center x, which is where the circle will be centered, squaring it, adding it to the y value minus the center y squared, and then taking the square root of all those. So that gives me the radius from this x and y location from the center of where my circle's at. Then with this if statement, I'm checking to see if the absolute value of my target radius, which I've set to 400, versus the actual radius of my circle, if that's a less than 0.5, then I'm going to set it to 1. So this is going to give me a thin line circle. Otherwise, I just set it to whatever the value was before. So if I run this process on here, you can see I get a nice circle. If I want to expand how big that circle is, I can open up this width. So I'll just set it to 5. So you can see the radius is actually in the middle of this line, but since I'm looking for the absolute value of the difference between the radius and where I'm at in the image, setting it to 5, this will actually be a 10 wide pixel line. The easier way to do this, there's actually a built-in function called rdist. So you can do this instead. This is just the radial distance from a center point. So it does that exact same function I described earlier. You can also alias lines and circles. So there's a function in here called distance to line. So I've given it 4 coordinates. You can see x1, y1, x2, y2. So that's 2 coordinates on the image, and I'm going to draw a line through that image and then check the distance to it. And then I'm computing a value based off of this distance to the line and dividing it by w, which is going to be the width of my line. So in this case, because I want the actual width to be whatever I have in here, I divide it by 2, because this is going to give me the same distance on either side of the line. It's essentially doing the same thing, the absolute value of that difference. And then I check to see if this value is less than 1. If it is less than 1, which means that I'm within the actual line, then I'll do this kind of blending, which I'll talk about in a second. Otherwise, it just gets what the image value is. And you can see what I'm doing here is actually an alpha blend. There's an implied one here. So I'm blending the image with this function here, which is based off of the distance away from the center of that line. I'm blending it between the value of 1 and the value of the image. So if I run this, oh, this image is, let me unstretch it real quick. You can see that the line is not just one solid pixel. As it gets further away from the center line, it gets closer to what the actual image value is. If I stretch it, it kind of blows it out, so it's hard to see here. You can do the same things with circles. This is an alias circle. Again, I'm taking the radius now and doing the same type of division based off of the width of the line. Oh, that one's off screen. So now you can see I have an aliased circle where it gets closer to whatever the actual pixel is the further away you get from your target radius. So those were a little more complicated. Does anyone have any specific questions about that?
David, where in the expression was that alias?
Okay.
I'm sorry.
Yeah, that's fine. So the alias is happening here. So here you can see I'm checking the distance from my target radius to the actual radius at any given location. And I'm dividing it by the width of what I want the line to be, right? So if I have a line width of 5, and so that's
Okay.
2.5 pixels away, right? So this turns it into a 0 to 1 from the center of that radius out to half of the width, right?
Okay.
And so so when I check against the the 1, then I'm just doing a blend between the target image and whatever that alpha value is.
Okay, I see what you're doing.
Yeah.
Thank you.
Sure. Any other questions there?
Eric was asking, and this is almost something we have to discuss eventually, but maybe, well, first, can you write the color star replacement script with instructions as to how to vary the mask and the ADU value so to replace white stars with color stars from another image? And I don't know if there'd be a one-size-fits-all to that. Josh asked him back, oh, create the masks first and then create the script, but
yeah, I mean the function is quite simple. So let me bring up the reduce purple stars here. So the function is once you have the star mask in place, so you definitely create your star mask first, right? And then once you have the mask, you would just check for a particular value, right? So I would just check to see if my target image is greater than a particular value, like in Josh's case, he wanted 240 in PixInsight, which I think I determined was about 0.935, since PixInsight uses a 0 to 1 range. And if it's greater than that, then I'm just going to replace it with the star image value. Otherwise, I'm going to replace it with the current value. I don't know, Eric, if that makes sense to you?
So David, maybe one thought on that is, can you pick a value from your star image instead of the regular image? And so if there's any separation from the background in your star image, pick anything that's like above 2 or I guess 0.01 or something above your average background sky value, and then use that value to replace spots in your actual image.
So yes, and let me write this up. So this is basically what you're describing. So if the value in your star image is greater than, say, 2 times the median of the image, the star background, then you'll end up replacing the data with the star image. Otherwise, you'll leave the data alone. And this median function, there's all sorts of functions in here. You can use the mean, the median. you can actually check for standard deviation and say, actually determine what this 2 value should be based on standard deviations if you wanted. So I think that would do essentially what you're asking.
That seems impressive, because if you can do that, and at some point if you can create a script that would avoid manually having to make masks, that would be pretty powerful. Although there's never any perfect one-size-fits-all, but
yeah, you'd probably have to vary a little bit, but I've actually found that a lot of these functions are a lot more useful without changing anything than I would have thought.
So that one looks like it could be pretty impressive.
It's not something I've done a lot, replacing the stars. All right, any other questions there? Let's move on to cross sections. This one's pretty interesting. So cross section is just actually taking the values through some sort of line through the image, and so in this case I've put a couple functions in a process container so they can run together, and I'll go ahead and run it so you can see what the result of that is. So here I'm just kind of drawing a line through the middle of the image and looking at all the intensities, and I'm turning that into a plot, a horizontal plot, not only showing what the color is, but actually making it so that you can see the color. In this case, the image has a lot of vignetting in it, which is fairly obvious, but it's a little more obvious here. So if I bring up the first portion of this one's pretty straightforward. I'm just taking the pixel value at a given coordinate, and so I'm taking it from the active image, and I'm going to give it the x coordinate of that image, but I'm always going to give it a single y coordinate. In this case, I'm taking half of the image height, so that whatever the height, wherever I'm at in the image vertically, I'm always going to give it the value from that center line pixel. So if I apply this here, you can see that it just takes those values and extends them up and down from that center line. So if I zoom in here, the center line somewhere in here going through the nebula. I could actually change this and instead take a line, I'll take a line from 237. So y coordinate 237 instead, which is somewhere up in this region up here. So you can see the variation isn't as great there, although you can still see darkening in the corners. The second part of this is turning that into a height. So here, this capital Y is returning the coordinate, the y coordinate, in the 0 to 1 range rather than in a 0 to height range. And I'm checking that against the inverse of the image value. So the image is going to range from 0 to 1. This y value will range from 0 to 1. If my image value inverted is greater than the y value, I keep touching the screen, then I'm just going to give it a value of 0. That says anything above the brightness level of this current pixel will get a value of 0. Otherwise, I'll just return the value. So if I apply this first pass again, we'll use not use the center line, we'll use the offset line. And I apply this. You can see it actually gives me a plot from that new horizontal slice through the image. So essentially what it's saying is that at this pixel value, this line had a particular intensity level. That intensity level, when I compare it to the height of the image from 0 to 1, it only goes up from that range 0 to 1 up so high in the image. I do the invert. If I turn that off, you'll see it actually creates a very interesting pattern on the top side. This is really quite interesting for checking, how bad your vignetting and different patterns might actually be in your image. So you can do similar things for, horizontal cross sections. So that's horizontal. There's a vertical cross section here like this. So that goes right through the nebula, and you can actually see some of the spikes through the stars. Those are pretty interesting little tools to be able to use. Any questions on that one? No?
Not yet.
So there are multiple ways to remove hot pixels. I started off using this, and I just really included in here just so you can see how it can be done. Here you can see I have a whole lot of symbols and actually a very long expression. So bring it up in the expression editor. See here, I'm doing all sorts of checking, and essentially what I'm doing is I'm making a window of 9 pixels, and that moves as the pixel math engine is stepping through every pixel. So you can see I'm getting the center line, x1 and y1, and I'm subtracting 1 from it for x0 and y0, and adding 1 to it for x1 and y2. The rest is clipping to make sure that I don't go past the edge of the image. And then I just return those values for all those coordinates. And in this case, I'm taking the median of those values, excluding the actual center pixel. And I actually take in this case, I'm using the bi-weight mid-variance rather than standard deviation to determine how far away I should actually be from the pixels, what value is allowable. So if I go over here and look at my image, you can see there's some hot pixels in here, and here. If I run this on the image, you can see those hot pixels go away, but nothing else is really touched in there, just a few hot pixels. I like doing this in particular because I think the bi-weight mid-variance function is more robust than standard deviation at determining outliers from a median value. So I've had better success with this correctly identifying hot pixels and outliers than the standard deviation functions that you'll find in like the cosmetic correction. So it's a little bit of a complex expression, but the gist of it is pretty straightforward. Really just taking a 3x3 box of pixels and doing this median and standard bi-weight mid-variation calculation on it. And then you can see I take that median value and I've got an F value, which is a factor value that I'm multiplying this deviation from the bi-weight mid-variance function, and if it goes over that or under that, then I just turn it back into the median value instead. You can do similar things with I've got a salt and pepper noise reduction, and essentially it's just the same thing, but I use a much more aggressive factor value in there. I usually use this with a mask. If I run it on the image, you can see it blurs quite a bit in there. So generally, I use this with a mask. If I see a lot of kind of salt and pepper noise in an image, and I use this function on there before I do anything else with the data, it does a little bit better job than some of the other noise reduction functions for removing that salt and pepper effect from the image. Any questions on that one?
You know, Told is asking, do you write these scripts yourself? Are they available to download? Do you buy them? Are they like actions?
um, I've written most of these myself. There's a few that I haven't. The cross-section one I saw online. I wish I could remember where, because I can't remember, so I didn't credit it here. But most of these are just ones I wrote. You know, I understand the math a little bit and just put in the functions. Like this one is just one I wrote myself. They aren't actions per se, but like you can see here, I have all these things saved off, right? So, you know, I've got this hot pixel remover. I technically do it in 2 steps. The first step is a very low aggression factor, and the second step is higher aggression. I do it in 2 passes because sometimes you'll have 2 hot pixels right next to each other, and this tends to catch those situations a little bit better if I do 2 passes. So you can save that function off so it can be repeated, right? And typically I have kind of a base project. Whenever you load up PixInsight, you know, I have a project that I saved off that has all these actions in it. So if I just run this, you know, function, you can just apply it directly to the image. It'll run, and then those hot pixels are gone. So they are kind of like actions in that respect. I haven't published these anywhere, but I can certainly put them online with the presentation data after this if anyone wants access to these. All right, any other questions about that data?
Josh and Tolga both say yes. They would love to download your processes. And I just want to say, I know when you buy Warren Keller's tutorial, he gives you a bunch of processes. And that's one of the valuable things about his tutorial, is the processes that come along.
Right. It's very useful to be able to save all these things off so they're repeatable. So the next thing on my list is the Halo model or Halo removal. So I posted about this one online, but I'll go through essentially, you know, how I did this. So it's pretty straightforward. I mean, really all we're trying to do is model what the halo looks like. To do that, I'm going to copy this image off, and I'll bring up Pixel Math again. And I'm just going to assign this image a value of 0. So that means every pixel in this image is going to get a value of 0. So now I've got a black image the same size and in the same color spectrum as this, which is a grayscale image. You can also do that doing a new image. You can create a new image this way and put in the width and height, but I find that a bit easier to do. So I'm going to rename this halo model. So this will be where we store the actual model of what our halo looks like. So the next thing we need to do is actually measure what our circles look like so we can actually recreate them. This is another one. If you can see the readout at the bottom of the screen, way down over in this area, you can see the X and Y coordinates. And I'm just going to kind of hover over where the extents of the circle are. In this case, I'm looking for this fairly large circle out here. So it's about 602 or something like that, and the other side is around 1340, somewhere in there. So I'm going to start logging that information. So 602, around 1340 for the right location. We don't have enough of a circle on top and bottom to determine where the center is that way, so I'm just going to guess at the center. And 270, 250, so somewhere around 265 is a guess. So I'm just going to put the value in there. And you can see in the spreadsheet, I have a function here to kind of concatenate all that mess together and put out something that I can copy directly into Pixel Math as symbols. But you could just copy, these values in X center, Y center, radius. And these are just based off of these values. The x-center is the average of these two. The y-center I put in directly. The radius is the distance between the left and right divided by 2. Those are all pretty straightforward. So now I need to measure the intensities of what that circle actually, how bright it is relative to the background, so we can actually subtract it from the image. So I'm going to draw a couple of preview windows. I'll see if I can get a little bit more of this. So that sits well within that first circle, and I've got another one for the background. And I'll bring up the statistics tool and do this in a 0 to 1 range. And I'm going to look at this first value. So I'm going to look at the mean. Since I don't have any stars or anything in there, I can just use the mean of that box. And I'm just going to copy that value off. And I'm going to paste it into my spreadsheet. In this case, I want it relative to the background, so I'm going to now measure the background, which is 2, preview 2. Take that mean value and put it in my spreadsheet. So I'm going to do that first value versus the second one. So now I have an intensity here, and you can see that fills out my little value over here. So now I've got everything filled out. I can copy my symbols in over here, bring up Pixel Math. I'll write my little equation. I'm going to check to see if my radius is less than the target radius. If it is, then I'll replace it with I. Otherwise, I leave it alone. So this says that anything within this target radius relative to the centers I've specified will get this value of I. Otherwise, it'll get whatever value is there, which in this case happens to be black. And I'm going to replace the image. So I should get a... Nope. Did something wrong. Oh, I have X center and Y center. Okay, so now you can see I have a circle over here in my other image. And typically what I do is I save off that function. You can see I put a bunch on the side over here, and I'll rename it, call it temp1 in this case. So now I can just replay that particular function whenever I want to. So if I do something wrong or change something, I can just replay it again. So now I want to subtract that from my image and just see what it does. So I bring up Pixel Math again. So I'm just going to take my active image minus the halo model, which is what I've called the other image, and subtract it. So you can see that it basically just dims that part. It gives kind of a hard edge. If I zoom in here, you can see there's the hard edge along there. You can actually try to model that, but I find it easier just to blur the image a little bit. So what I'm going to do is bring up the convolution tool. And here I'm just doing a 23 by 23 essentially straight Gaussian blend. The circles are pretty big, so they're you can get away with a fairly large blur here. So you can see that really blurs the edge of that circle quite a bit. Now if I subtract the model, it looks a little bit cleaner. You don't get that hard edge through there. So that kind of covers one circle. Now let's try to measure the next circle. I'll unsharpen, unblur that one. Now let's measure the next one. So you can do it this way. So in this case, there is some gradient here, between, in this direction anyway. So the last time I did this, I actually measured relative to the previous value. So in this case, I'm just going to move this guy up and measure this one up here. Bring up my statistics again. So the mean of the preview 1 box, I'll take that guy. I'll subtract out the difference with the secondary ring. But then on top of that, I want to add in the value of what that secondary ring was that I calculated. So I'll just add in that value there. Now I've got an intensity 0.0075. Let's measure that inner circle. And here I'm going to I'll use a little trick. If I'm having trouble figuring out exactly where the lines are at, you can just put in some lines, right? So I'm going to check to see if there's a line somewhere near, we'll do 603, or this other side over here, we'll call that 1312. And you can also say if y is a particular value, do around 250. So if any of my coordinates are equal to those, then it's going to have a line at that location. So I'll say 1, otherwise $T. And now I should get 3 lines, 2 vertical and 1 horizontal. And then I can actually just visually inspect and say, does that look right? It's a little too far off. Maybe this one's a little bit too far in. I want to move this line out, so maybe I'll do 315 here, so I'll back that one up a bit. Do 315. That looks a little bit better. This line looks maybe a little bit high in the image, so add a little bit to that. That looks pretty good. Those lines look like they intersect at the tangent of the circle, so I'll use those values. That's 603, 1315, so I'll just put those values in. And the y value was 255. So now I have my values. I'll bring up this and actually put those in. And do this, and I will apply this to my image, so you can see I'm doing pretty much the same function again. Apply that here, so now I have a brighter circle within that other circle. So I'm going to go ahead and soften it before I subtract. Then I will subtract the model. You can see the second ring was a little bit too dark, so I need to lighten it up a little bit. You can go back and recalculate things, or you can just change the value. Maybe it should be, I'll do 6.5 instead. Right. I'll back that up. Apply that again. Blur the model and then subtract it. Looks pretty good over here, but a little too dark over here. You can just kind of sit there and play with these things until you get something pretty accurate. Soften it up again. Oops. That's looking a little bit better. Still a little bit dark over here in the corner. This is essentially all you're doing. You're just trying to draw circles on one image that match the circles on the other. And that looks pretty good. I accidentally removed my PixInsight icon, but I can actually bring it back up if I look at my halo model and go back to the step before. So all your steps are saved off in the history, so now I can just save it off and I don't have to worry about it. So you can keep going that way. I've done a bunch of these beforehand. So I'm going to, I closed my star model, halo model. Let's see. So I'm just going to apply these to this image here. So you can see the inner circles in this image were a bit darker, so I'm modeling them a bit darker in here too. There are also some outer rings that are a little bit brighter. So I'll apply those. You can see in this case I'm actually looking for a centerline radius and doing similar to what I did before, where I'm drawing a ring rather than, let me back one of these up. I'll back up both of the rings. So if I crank up the intensity quite a bit, you can see what the ring looks like. So you can see I'm drawing a ring here that's kind of equivalent to this brighter ring in here, and I'm just doing that by looking at the distance from the radius to my target radius and checking to see if I'm within that, similar to how we drew circles before. Let me kill that. Apply this for the outer one, for the inner one, and then I'll soften this model and subtract it from the image. Oh, forgot to rename it. So that looks pretty good. So there's still hints of where the halo was, but they're not too bad. You can sit there and tweak this a lot. I'd actually gone through a few more passes to try to, it's darker in this area than it is over here, to try to add some of the gradient into it. But at a certain point, it gets, too cumbersome. So I actually ended up just stopping there, and we're actually going to copy this image off and stretch it. And we're going to use that as a mask for applying some corrections here. So apply that mask to our image and invert it. So now all the brighter portions are better protected than the darker portions. So when I go in and try to clone stamp over these things, I'll be a little better protected that way. So I'm just going to go through and finish cleaning these up with a clone stamp. I'll take a sample fairly nearby so I get my intensities pretty close. Let me back out a bit. And you can just basically go through and paint the area to try to remove the hints of where some of the halo was. So you can see that's basically disappearing over here. Oops. I'll use a much larger brush in this area and drop down the opacity quite a bit. And you just basically paint away the edges of where the stuff was at, so it's no longer visible. And once you do enough of that, you'll have an image where the halo basically isn't visible anymore. Let me finish that off, and I'll bring up this one. This is the one that I finished beforehand. So you can see that not much of the halo is left after I finished kind of cleaning up the fringes of where the sharp edges of the halo were. I know that one was a fair amount. Are there any questions on that one?
The questions that were asked were answered.
Excellent. So I have one more here. Occasionally you come across situations where your calibration data isn't working. Ennis was posting on the forum the other day, and he had some very interesting banding going on in his image. And so it was interesting to try to check to see where that sort of stuff was coming from. So I've got some of his data here, and I'll just shrink this down a little bit so we can fit them all. And this will also actually help explain how the calibration engines actually work, what the math behind them is. So this is a single light frame. I'll take the stack. This one is a stack of all of the light frames in his image without any kind of registration. I was trying to get an idea of what the actual patterns looked like in the image, regardless of the data. This is what I'd called a nighttime sky flat, essentially is what I pulled out of this. But let me bring up my... I think I lost the calibration one. I have too many icons in here. Okay, there we go. Full calibration. So this is essentially what the calibration looks like. I'm going to rename this guy Light. This is my light frame, stand-in for a light frame. This is my dark, my bias, my flat, and this is the function to do calibration. So you can see I'm doing a bias subtraction from the light, the dark. These were all straight averages. A bias from the minus from the flat instead of a dark flat. We didn't have a dark flat here. Then I'm subtracting the bias subtracted dark from the light. PixInsight can do scaling. So if you're actually doing scaling, it would actually look something where you'd have some scaling factor in front of the bias subtracted dark in place here. I have to adjust the flat by the bias. Normally, you're already bias subtracting your flats before you're using this. In this case, I didn't want to do that. I wanted to kind of play around with the values. So the flat, bias, and darks are just straight averages of all of their subframes. But if I apply this to the image, it did some subtraction, so the histogram stretch was not quite right. You can see that the flat didn't apply perfectly, and he has this banding in here, right? And you can see that there's some gradient in this image. Is what that's kind of what I suspected was the problem. But even when I corrected the image for the gradient, the flat, while it applied here correctly, still didn't remove the banding, and that led to the question of which of these the banding has come from. So you can actually go through and check this type of behavior beforehand to see what's going on there. In this case, the banding is definitely coming from the flat, and I ended up stretching the data enough that you could see the banding pattern in the flat was actually different than the banding pattern in the bias or the dark. And what I ended up doing to calibrate this was I essentially just took this stacked image from all his lights and creating a flat. You can actually see the flat pattern in it, but the banding is actually different in here between these two. So I ended up pulling turning this light stack into a flat frame to use with calibrating his data. All right, I think that covers everything that I was going to present. Like I said, I have all these in the presentation, so you can see the calibration math, purple star removal, pixel cross sections, rendering, and I will post this after the presentation on the Google Plus site, and I'll probably put it on the YouTube as well. And I will put this PixInsight project file out there as well, so you'll have access to the all these functions here, these desktop icons, so you can play around with them. So, are there any questions?
I don't have any questions. If anyone else does, they're welcome to shout them out. But I do want to say thank you, David. That was great. And I was admiring your process icons as soon as you opened up your screen.
Right.
Anyone else have any questions? Reminder to the viewers out there, you can type them into Q&A if you have any. Now's your chance. Benjamin Dye, what is your favorite color? I don't know.
Not green?
Yeah.
I don't like green stars when they show up, so not green.
Yeah. SCNR.
Mm-hmm. And by the way, that's essentially where that min function, when I was doing the pseudo, the synthetic green, that SCNR, this is effectively what it does. You're doing the min of the green relative to the red and blue, and then you're doing a blend, an alpha blend with it.
Hmm.
Or at least the that one particular function, where is the SCNR? The average neutral function is what that describes.
Mm-hmm.
So when you do an average neutral with the amount, this amount is essentially that alpha value, and then you're just doing the min between the green value and the red and blue.
It's interesting, as you were going through a lot of the functions, I'm thinking to myself, oh, well, that's how that particular process works. Is most of it based on pixel math? I guess it is. I mean, it is all pixel math.
Yeah, at the heart of any of those processes, you're just doing some sort of pixel math. Now, obviously, at a certain point, it gets complex enough that it doesn't make sense to do it within the pixel math tool itself. Some of the hot pixel remover functions and stuff like this, these are kind of borderline, right? This is probably easier to just take it and turn it into a script at a certain point.
Right. Well, like DBE, for example, I could see a script written pretty long, but that could sample a bunch of spots and then take probably the mean value and then redistribute it, so to speak.
Yeah, absolutely. Yeah, you could even take it as far as doing a plane of best fit or a curve of best fit if you really wanted to.
Mm-hmm. Yeah, it's interesting. PixInsight it's just the limitation of your knowledge of the program with what you could do with it. We had a good number of viewers on tonight. I think I saw like 10 max, which I think is pretty good. That's 10 outside of this live room. Pretty good, competing with the Super Bowl. And for quite a niche topic, even for astronomy or astrophotography. For everyone out there, I again, thank you, David. And I do want to say I'm planning a presentation next week on big images from little telescopes. So for all those, for a lot of newbies and for a lot of people that have been doing this a while, you get some nice images out of small telescopes. And I'm going to do a presentation on that to give you an idea as to what you can get out of it. Thank you again, David. I am going to say goodbye to all of the YouTube viewers or to our people out in that live thing. I'm going to check Q&A one more time in case you asked a question. Okay, is there a good source for learning more about pixel math? John is asking, John Kellum's asking, he doesn't own PixInsight yet.
Sorry, on mute there. There are some good sources, and let me bring this up here. These are actually in the back of my presentation. I have a few links in here. Am I sharing that? I'm not sharing that. So these will be in the post I make for this. But there's some resources on the PixInsight site, on the forums. You know, like the math for the blending modes for PixInsight. I just pulled those from Wikipedia. Harry has some great tutorials. There's a whole bunch of stuff out there. It's not the easiest to find necessarily in all cases. Warren's videos I've heard are very good, although I've never watched them. But there are definitely some resources out there, and like I said, I'll post this so you can have access to the list that I have here.
And does anyone know whether Pixel Math is available on PixInsight LE, which I think is a limited... I think it's a free version of PixInsight.
It is technically available on that version, but it's very limited in what it can do. It's from like the 1.2 version of PixInsight or something like that, so it's very old. It looks substantially different. You can't do like parentheses in your equations or anything like that, so you're limited by order of operations. And
okay.
But I think Sean found that. I didn't know, that was even available in there. Sean found that the other day.
Yeah, and I think he said DBE is available on it.
Yeah, that's a really good one. Although I think you actually have to do the subtraction manually. It just creates the background model.
Well, that's not too bad.
Yeah.
All right. Hope that answered your question, John. And thank you guys out there. We'll be back next week. And for now, I'm just going to have to say goodbye.